Thank you so much. It's great to be here. Hi, everyone. I'm excited to talk today about data-centric AI in practice and what we've learned at Scale AI working with hundreds of computer vision teams about what it takes to make machine learning work really well in production. So by way of introduction, my name is Russell. I'm the head of Nucleus at Scale, which is our dataset management product that helps teams improve their machine learning models by improving their data sets. I joined about a year and a half ago when Scale acquired my computer vision startup called Helia. Before that, I was a machine learning scientist at Tesla on the autopilot team, responsible for the core vision neural network. And before that, I was a researcher in the Stanford Vision Lab working with Fei-Fei Li. So this concept of data-centric AI has gained a lot of traction recently. And it's the observation that making machine learning and computer vision and all other types of machine learning work well in production involves so much more than iterating on the models and iterating on the code. And in fact, we're increasingly focused on iterating on the data set. And data-centric AI is the discipline of systematically engineering the data used to build an AI system. Over time, as machine learning architectures, hyperparameter optimization schedules, learning rates have become increasingly explored and figured out, we have a pretty good set of foundational building blocks that usually just work when you plug it in to a new machine learning problem. And so production teams are shifting their investment and their focus from model development to data development. And I would argue a very important part of why this is necessary and why this is happening is that most machine learning problems we encounter in the real world are long-tail distributed. As an example, Berkeley Deep Drive dataset is a public dataset for self-driving cars, and it shows a very classic data distribution that we see in all types of computer vision applications, where the most frequent classes occur quite frequently, and there's an exponential drop-off in frequency as we get to rarer and rarer classes, the deeper and deeper edge cases, and you'll find many orders of magnitude more cars than trains or buses. And this is one of the things that makes machine learning in production so challenging, that we have to work well on all of these edge cases, but they're so inconsistently represented in the data we collect. This has important implications for every part of the machine learning lifecycle. Not all data is created equal. When you're prioritizing what to annotate, would you rather annotate the image on the left or the image on the right? Well, if you're the annotator, it might be easier to annotate the one on the left, but as the dataset builder, it's much more valuable to have the image on the right. Should that be a car? Should that be a truck? How do we label cars inside of other cars? These are the types of edge cases that make real-world computer vision so challenging. We can do this in a targeted manual way. We can also prioritize annotation data systematically. There's an entire area of literature called active learning focused on figuring out strategies given a model or set of models to find the right unlabeled data that, when annotated, will drive the biggest model performance improvement. And so a very common plot in this type of literature is to see an estimated annotation budget on the x-axis and to measure how much accuracy can you get under that annotation budget on the y-axis. The baseline is always random sampling. We'll just collect some data, send it off for annotation, and train a model. Very consistently, there are strategies you can employ, active learning strategies, that meaningfully outperform random sampling. This is one from a paper called Active Learning at ImageNet Scale. But data curation is not the only problem with adopting data-centric AI. The reality is not all data is well labeled. And this is one of the most understudied problems in academic literature, because we have to have standard dataset benchmarks to be able to compare research results. And all of those research results, by and large, tend to assume that the data is annotated correctly. And all evaluations are with respect to those annotations. But those annotations aren't entirely correct. It's estimated that around 6% of the validation set of ImageNet is mislabeled. There are similar figures for many other public data sets. What makes this problem worse is that labeling errors are most common at the very tails of the data distribution. Those edge cases, we're not really sure, according to some ambiguous set of instructions, what we should do. Should we label that image as a single truck, as a car, as a set of cars? It's really hard. It depends. I would also like to note that cleaning bad labels is one of the most frequent ways we see to systematically drive model performance improvements. Again, very hard to study in an academic setting because the test set also has bad labels. So actually, sometimes cleaning the labels in a training set makes your performance worse on the test set because you start to underfit the annotation errors in the test set if you do that. But in a real-world setting, we don't care about that. We care about actual performance, actual results. This is an example from ImageNet, labeled as a feather boa, which is maybe a chihuahua in disguise, but very clearly a chihuahua. There's an interesting relationship between the labeling accuracy of a data set and the value of that data set. And it turns out you can derive mathematically that there's a roughly quadratic relationship between the error rate and the value of a data point. So as your error rate goes up linearly in annotation accuracy, your model performance drops quadratically, which is one of the reasons it's so valuable to invest in high-quality annotation. Beyond building the data set, making sure it's well curated, making sure it's well labeled, we're really just getting started, because that gives you your inputs needed to build your first model. But increasingly, under data-centric AI, we think of deployment not as an event, but as a process. As Andrew Ng put it, deployment is a process, not an event, and beginning deployment only marks the beginning of collecting more data and to keep on updating your model. And we see this all the time at scale where I work, where we partner as an AI infrastructure provider and labeling provider to companies of all sorts. They increasingly view model deployment as the beginning of a journey. And the performance of that model is not only important in and of itself, but it's important to improve the ability to mine the next round of data to annotate. This is an evolving system. We're trying to get the best possible accuracy as quickly as possible. And so given all this, we need some way to measure ML team progress. And I don't mean on an individual model level. I mean, as a team, how are we doing at building a data-centric AI workflow? How are we doing at improving our velocity, improving our time to production? And so in brainstorming ways to actually measure this, I thought actually to another type of progress measurement that's much more broad than machine learning. It's a way to measure progress of civilizations, and it's called the Kardashev scale. Has anyone heard of the Kardashev scale? Quick raise of hands. OK, we have about 10, 15 hands, I would say. So this is a scale invented by an astronomer, Nikolai Kardashev, in the 1960s, trying to quantify how advanced a civilization is. And he came up with 3 levels of civilization. There are type 1 civilizations, which are able to harness the energy resources available on their entire planet. And he chose energy as the base metric of civilizational progress, because in many ways it's an input to everything else we do as a civilization. So type 1 civilization can harness all the energy on its planet. We are not yet at type 1 civilization as humans. There's a lot more energy hitting Earth than we can reliably harness, but we're making slow progress. A type 2 civilization harnesses all the energy in its solar system, everything in its host star. And a type 3 civilization, maybe one day, can harness the energy in an entire galaxy. And I think there is some analogy for ML team productivity. What we see is there's pretty clearly around 3 buckets of teams that are at different stages of their AI journey. Type 1 ML teams, type 2 ML teams, type 3 ML teams. The first axis of measurement is around deployment velocity. A type 1 ML team will often train a model ad hoc, deploy it, see how it does, and maybe get in some monthly cadence or ad hoc cadence for shipping improvements to those models. But it happens with dedicated focus, dedicated input, and it's not on a rigorous operational schedule. As infrastructure improves, as data practices improve, as the team grows, there becomes a richer operational cadence. Maybe you're deploying weekly as a type 2 ML team. And the teams with the most sophisticated infrastructure, who are the farthest along in building out their machine learning stack, tend to do continuous model improvements. So no intervention needed. We're always retraining, always getting better, always collecting new data. Another clear axis is in data curation. We all start with random sampling because it's a simple baseline and gets you somewhere. But very quickly, when those machine learning models get deployed into the real world, we learn that random sampling is not good enough. And we get bug reports from customers We get complaints from our bosses. Why didn't it work here? And to be able to fix all those, we need to do targeted data set improvements. We need to mine for the edge cases where we're currently struggling the most. And type 2 ML teams have this process to manually improve the data collection process, manually improve the curation process on targeted edge cases. The most sophisticated ML teams do this in a highly leveraged way where they can take quick feedback and turn it into massive curation campaigns to systematically improve performance on that edge case and make sure that performance doesn't regress in the future. But also use automated active learning so that the pipeline of data that's coming in can get prioritized according to what's going to be most valuable. The third is around annotation quality. When teams start out, usually they don't have a QA process for annotation. They label some stuff themselves, maybe they get some annotations from somewhere else, and they go with that. But as teams realize the dramatic performance improvements of super high quality data on model performance, they start to implement their own QA or use some service to provide QA. And that type of QA can significantly improve performance, especially in the edge cases where those labels are most likely to be challenging. The type 3 ML teams do this with their models fully in the loop. It turns out your machine learning model knows a lot about whether a label is likely to be correct or incorrect, and we'll cover what that actually looks like later. Maybe most importantly, there's a question of where do the improvements in a machine learning stack come from? At the beginning, it's the machine learning scientists who are driving those improvements. You're running the experiments, you're collecting the data, you're training the models, you're getting things off the ground. But as teams grow and as processes mature, as the data becomes more and more central to the improvement lifecycle, machine learning engineers will work hand in hand with data PMs, data teams, folks who specialize in collection, quality, curation to make sure that performance improvements are driven in the areas where it's needed most. And where teams move towards, and there are very few teams like this, I would say, today, but where the industry is generally moving, is in this type 3 ML team that drives almost all of its machine learning model improvements, not from engineers, not from machine learning scientists, but from data teams. Once the infrastructure is good enough, Andrej Karpathy famously called this Operation Vacation. Your entire ML engineering team should theoretically be able to take a vacation. And as long as the labelers keep labeling and the systems stay running, they should be able to come back to a higher performing model. And I think this is a useful North Star for infrastructure and processes for machine learning teams as they continue to grow and develop. And these observations have been motivating to us at scale in building our product suite, because we see teams face these challenges again and again. The product I work on, called Nucleus, is a dataset management platform designed to help with two things. The first is to figure out where in the data distribution, where in that long tail, are the models really struggling the most. It's not enough to say we're at 80% accuracy and now we're at 82% accuracy. Maybe your most critical customer no longer works. Maybe a complaint that you got fined for, a complaint that you needed to deal with in the past has reemerged worse than before. You need to know the qualitative failure modes of your machine learning models to have very, very high performance guarantees. So once you can find where your model is struggling, the next important part is how do you fix the problem? And we see two common paths for fixing the problem. Number one is better data curation. Number two is better labels. Nucleus helps you do both those things. And rather than doing much of slides about it, I figured we'd show a live demo, although the internet in this room, I make no guarantees on. We'll give it a shot to see what this actually looks like in practice. So this is what Berkeley Deep Drive looks like in Nucleus. We can see a lot of examples, some affordances for searching it, and we could wear the hat of a machine learning engineer who's getting reports that their safety drivers are intervening frequently when there are trucks at nighttime. We keep something in the stack is not working. We need to debug what's going wrong. How would you solve this problem? Well, the first thing we might look at is that data distribution. Do we even have enough truck annotations in the first place? We can see the Berkeley Deep Drive distribution is pretty skewed, but we have around 34,000 truck annotations. That's enough that we should be able to learn something about what a truck looks like. All the plots in Nucleus are fully interactive, so you can always go from aggregates to specifics. So here, we're looking at the data set filtered down to only images with at least one truck annotation. This is useful, but not sufficiently specific, because we were told the problem is happening at nighttime. And so one of the core parts of Nucleus is a very flexible querying engine that ingests arbitrary metadata, model prediction data, and annotation data, and makes it searchable. So here we can see all the images with at least one truck that were taken at night. This is useful, but we're doing this for the purpose of debugging a machine learning model. I see some people trying to see in a little more detail, so we can zoom in a bit. We're interested in debugging our machine learning model, not just looking at the ground truth annotations. And so fortunately, Nucleus is a developer product. It's easy via API to add your own machine learning model predictions in addition to your ground truth. If we were to add our own model predictions, we would then go back and be able to see them in the interface, filtering alongside our ground truth. So here I'm looking at, in green, our annotations, and in red, our model predictions. So I can start to get a qualitative sense of what looks right and what looks off. But it's much higher leverage to see systematically where are we doing well and where are we doing poorly. So if we go back to these charts, we can see metrics generated automatically that tell us where our predictions and ground truth agree and disagree. So many of you are probably familiar with a confusion matrix, which is showing the classes that our ground truth and models agree with or disagree with. We'll also compute the IOU distribution. How tight are your bounding boxes? How much overlap do they have? What's your precision recall curve on everything or on a specific class? And many other metrics you would expect. But again, it's not enough to just get these aggregate metrics. You have to dive into the specifics in data-centric AI to make your actual data better. So let's look at the details. We can see, for example, in this confusion matrix that the truck class in ground truth is often confused as a car in our model prediction, 27% of the time, it looks like. What's going on there? Well, we can click on it and try to figure out what's happening. This is every prediction in my data set that my model considered a car, but my annotation considered a truck. Let's see if I can notice any patterns. Right away, I can see that a lot of these are pickup trucks. Maybe that's ambiguous in my taxonomy. Are pickup trucks cars or trucks? I don't know. But finding the qualitative examples like this where the model is failing is critical to improving the performance of a computer vision system. So we can do this to use our data to debug our ML models. But we can also debug our data with our ML models. So instead of trying to figure out where's the model wrong, we can also figure out where's the data wrong using the model. And so for example, this is a query showing all of the annotated images in my data set where, according to my model, it's a false positive. So there's no ground truth, but there is a prediction. And we're looking at just car false positives right now. And we're sorting them by model confidence. And when we look at these, one thing that stands out to me is that these really look like cars. Why are these considered false positives? Well, let's dig into it. And this is all real public data on the Berkeley Deep Drive dataset that we use for research as a community every day. You can see here, if we hide the model predictions for a sec, that all the annotations look pretty good, except we're just missing an annotation over here. There really should be an annotation over here, but there's not. And so that's being considered a false positive in our model. It's affecting our training process, but it's actually an annotation mistake. And so if you wanted to in Nucleus, you can easily review this as an annotation mistake. You can send it to Scale or your own provider for fixing those annotations. But we can do this very systematically, just going through examples one at a time. What's wrong here? Again, it looks like we've missed annotating a very clear vehicle in front of us. And this is not an isolated incident. So being able to do this sort of bulk data cleaning with your model in the loop and figuring out where in the data distribution your annotations might be wrong, in addition to where your model predictions might be wrong, this is huge for being able to drive performance improvements, especially in the long tail. But once you find those issues, you have to actually drive those performance improvements. You have to actually fix the problem. So how do you do that? Well, I'll talk through a recent example we saw where, based on some model debugging, we discovered that a machine learning model was getting a lot of false positive predictions of traffic lights. When we dug into it, we realized that it was confusing the lights on police cars as traffic lights. How do you fix a problem like that? Ideally, we would look through our unlabeled data to find many more police cars. The only problem is that we don't annotate police cars in this taxonomy. We just have cars and trucks. So we can't really query our model predictions to say, hey, where are the police cars? How can you solve this with Nucleus? Well, one thing you can do is you can run a natural language search. So instead of querying on structured data, we can just look in natural language for police cars. Under the hood, this is powered by clip embeddings, which produce aligned vectors between language and images. When those vectors are nearby, it's likely that they correspond to the same underlying concept. And so we can find right away, oh, yeah, it looks like we can see some police cars here. Maybe I want some more images of daytime, so I'll just add that. And focus on the bright police car images. This is great. This is really helpful. It doesn't depend on annotations being present, right? We're just looking at the raw underlying pixels of the image and whatever is the natural language query. So we could theoretically run this on our unlabeled data, find a lot of police cars, prioritize them for annotation, and fix the problem. But if I look through these examples, I can tell not all of them are police cars. There's some. There's a police car here, one here. That looks like a bus, not a police car. So it's not as accurate as I might like. What you can do in Nucleus is start with a single image or set of images and create what's called an auto tag. Think of this as targeted data curation on a specific class of interest, where in a few clicks, we're going to train a binary classifier inside Nucleus to recognize police cars from non-police cars. So my police car tag with a few seed images has actually kicked off training a machine learning model that is now resorting the data set according to what it thinks is going to be informative for me to tell it about. So I can see right here, we've got some police cars right away. But once again, we have this handicap bus with a blue stripe that's white. So I see why it was confused, but that's not a police car. And so by skipping that example, we're given an explicit hard negative label of what we mean by police car versus not. So we can go through and say, yep, this is what I'm looking for. This is a fire truck. This is not what I'm looking for. And relatively quickly provide very, very useful supervision for the exact concept we're looking for and the concept we're not looking for. And when I hit refine auto tag, Nucleus in real time takes the examples I labeled as positives, takes the examples I didn't label as negative, retrains that model and re-inferences it on the data set. This is happening in real time to provide another set of images that are going to be really informative for me to label. And it turns out with basically 2 rounds of doing this, you end up with surprisingly high precision binary classifiers that you can use to prioritize unlabeled data for annotation. So I'll go through, say, yep, these are the police cars I'm looking for. These are the ones I'm not looking for. And we can go ahead and we can finish and commit the auto tag. And after a few minutes, when we hit commit, that score, police car likeness score from -1 to 1 will be written on every item in the data set for all the data that's there now and all the data that's added in the future. And so with primitives like this, we can, as a team, really do targeted mining of the long tail. Mining of the classes we're struggling with, of the scenarios we're struggling with. Even if we can't articulate in rigorous taxonomy definitions what we're looking for, we can just show a few examples and make it better. And so for an auto tag that was already committed, we can look and run a search. For example, show me the cases where our auto tag for police cars is scoring greater than 0. And we can see there's a lot of data here, a lot of relevant data. Furthermore, we can refine the query to say, hey, I only want the unannotated images because we're trying to prioritize stuff for annotation here. Filter it down, create a subset of our data that we then send off to annotation. So these are some of the processes that we see teams adopting to improve performance on targeted scenarios and to develop a more data-centric workflow. Thank you so much. With that, happy to take any questions.
Great job, Russell.
Thank you very much. Very informative. 2 quick questions. It seems like what you've described is essentially that all the examples you described is very imbalanced data. So would you recommend using undersampling, oversampling, SMOTE for data augmentation, that approach, or would you recommend something else?
It's a great question. Many approaches work to varying degrees. What the literature that I've seen suggests is that among those, the first thing to try is oversampling rare data. This tends to work a little bit better than loss weighting of rare data. So oversampling rare data first. But what's much better is if you can just collect more. And unfortunately, most computer vision teams are in the regime where they can collect a lot more data than they can actually label. So once you've got your existing data set, I would say oversample it, maybe experiment with loss weighting, maybe experiment with more aggressive data augmentation, but really focus on how do we change our data distribution to solve the problem.
The other question is, does self-supervised learning help you label data more accurately? What have been your experiences with that?
Yes, I would say self-supervised learning is a critical ingredient for high accuracy, high quality annotation pipelines. Even the demo we just showed of natural language search, I mean, that's dependent on a model that's trained in a self-supervised fashion. So it can provide really strong baseline features to prioritize high value rare images or videos.
Thank you.
Thanks, that's a great demo. Just looking for more info on the ML cycle, right? If I look at Nucleus, now you have a platform, you build the model. How it integrate with the other platform, let's say Azure Cloud or Hadoop ecosystem for the full cycle of ML development?
Absolutely. So our philosophy for product development at scale is to build individual tools that are extremely useful in and of themselves, integrate nicely with each other, but can be swapped for any other systems at any component of the stack. So you can sort of pick and choose what systems you want from Scale, what systems you want from Azure, what systems you want from your internal tools, et cetera. So we have many customers integrating Nucleus with Azure. It's all typically API driven. You're ingesting your labels, your data, your unannotated data, your model predictions, and then from there exporting what you need to train your models.
All right, to Russell Kaplan, head of Nucleus at Scale AI. Thank you so much.
Thank you.
Really appreciate it.